Welcome back to this very episode. I will be explaining Dalton's law of partial pressure. So for Dalton's law of partial pressure, it talks about gases. Since you have seen pressure here already, you know that we're talking about gases. Gases that are not chemically combined. So for gases that are not chemically combined, the total pressure, which is the P total, is equals to the sum of the partial pressures. So for gases that are not chemically combined, the P total is equals to the sum of the partial pressure. So that means if you are given, for example, let's say the first pressure is 0.5, partial pressure rather, 0.5 atm, the second one is 1 atm, the third one is let's say 0.8 atm. Then if you are asked to calculate the Dalton's law, which is the P total, then what you're expected to do is P1 plus P2 plus P3. And what's our P1 here? P1 is 0.5 of the partial. These are down the partial pressures, please. Then here is 0.8. So that will give us 1.8, 1.9, 2.3 what? ATM. As simple as that. So that's just for Delta. This is the only thing that they possibly explain in partial pressure. Then partial pressure will also lead us to a concept called the mole fraction. And this mole fraction is denoted by the symbol S. I repeat, partial pressure can also lead us to the concept of mole fraction, and this symbol S is for mole fraction, whereby S is equals to P1 all over what? P total. It's very easy. So this P1 can be in form of the given pressure, while this P total will be the sum, which is the total pressure. This can also be a partial pressure, while this one will be the what? The total pressure of that particular gas. So let me give you a particular equation. Let's try it out. So let's look at this equation together. This is a particular question regarding mole fraction. This is not for partial pressure. I said Dalton's law of partial pressure is actually linked to mole fraction and is denoted by this symbol S, whereby I have P1 all over what? P total. So let's look at this equation together. Calculate the number of mole fraction of neon. So what's the formula for mole fraction again? S is equals to P1 all over what? P total. And we are told that the total pressure is, let me write PT as our total pressure, is 1.0 atm. Then our partial pressure, which is P1, is equals to 398 what? Torrent. If the pressure is 398 torrent. Now look up. As a good chemist, you are not supposed to solve like this. Is that you convert ATM to torrent or you convert torrent to ATM. So for example, if I want to convert this to torrent, I will multiply it by 760. So let's say times 1.03. So let me push my calculator. 1.03 times 760. My answer is 782.8 torrent. Now, both of them, they are now in torrent. Please take note. No matter what, your P total must be greater than your partial pressure, which is your P1. So from there, I will have 398 all over what? 782.8 all in torrent. Then remember, this one here is torrent, this one here is torrent. So if I have something like that, 398 divided by 782.8, yes, my answer here is 0.5. We have 0.5. Please take note. Mole fraction is unitless. It has no unit. So out of all the, what's it called again? Out of all the gases, which is kinetic theory of gases, the one that explains kinetic theory of gases, Boyle's law, Sharp's law, the one that is unitless is called the mole fraction. So mole fraction has no unit, and our answer here is what? 0.5, not 0.5 torrent. Please, you are expected to leave your answer at 0.5. Now let's assume that I want to solve this using ATM. So that is to say, I will divide this my answer by 760. So if I have 398 divided by 760, let me check my answer. My answer is 0.5. So I have 0.5, let me just say 0.52. So from there, 0.52 all over 1.03. Let me divided by 1.03. Our answer is also 0.5. So please, either you convert to torrent or you convert to millimeter of mercury, but before you solve, make sure your two pressure must be in the same unit, so that you can cancel out the two units, giving out a unitless what quantity. So that's just everything about Dalton's law of partial pressure. Okay, welcome back. In this particular episode, still continuation of the video rather, I'll be explaining Graham's law of diffusion and effusion. So Graham's law, in our secondary school we know of diffusion, but this very one now, a new one was introduced called effusion. So effusion is more of, for example, now this is a closed container and we have hydrogen gas here, or someone polluted in this particular environment. If gases can escape, the process of at which gases escape through this small hole, that's what we call what? Effusion. And then if someone polluted in this particular environment, before you know, the gases will be spreading, moving until it attains what we call uniformity. That's what we call what? Diffusion. So effusion talks about gases escaping from a closed container through a small hole, while diffusion is talking about the movement of a gaseous molecule or gases from a region of higher concentration to a region of lower concentration until uniformity is attained. And Graham's law of diffusion talks about the rate of diffusion of a gas is inversely proportional to the square root of the what? Of the molar mass. That is the formula for calculating whereby at the end of the whole thing you change this, but we are not after that. I want to show you something real quick. A question might come in this format. Arrange, they won't tell you to do most of all these secondary school calculation. This is how you see your questions. Arrange the following gases in order of their increasing rates of diffusion. We have hydrogen, we have oxygen, we have chlorine, we have CO2. So first of all, what is the atomic mass of hydrogen? Here is 2. 1 times, they will give us 2. Oxygen is 16. Here will give us 32. 16 times 2. Here will give us 72. That's 35.5 times 2. That will give us, is it 72 or 71? 71. Then carbon is 12. Oxygen is 16. That's 32. That will give us 44. So now the question is, if you have gotten to this, the question is, which of them has the lowest atomic mass? Hydrogen, followed by what? Oxygen, followed by what? CO2, followed by what? Chlorine. So the rate of diffusion increases with decrease in atomic mass. So that means the lower the atomic mass, the higher the rate of what? Of diffusion, the faster it will diffuse. So that is for that. So hydrogen will diffuse faster compared to oxygen, compared to CO2, and compared to what? To chlorine. This is just all about the rate of diffusion of a gas. But please take note, that will take us to the, I gave you a formula, a graphical representation like this, when we were talking about ideal gas law. And I said, in the real sense, there's no gases that behave ideally at all temperature and pressure. That is to say, at any given pressure or any given volume, the number of moles will be equals to 1. The formula is PV is equals to nRT, whereby N is equals to PV all by what? RT. So I'm not telling you that the number of moles is always 1 for any given pressure, any given value for pressure and volume. It is not really possible. So if it is not possible, that means you are going to have negative deviation or a positive deviation. Now, for you to say that we can't really have, which is, if the gas is not ideal, that means it's a real gas. So it's either you have ideal gas or what? Or real gases. So if the gas is not ideal, we can say it's a real gas. So, and like what I said, there is no gas. I can say, okay, most gases, they are not ideal, so that means they are real. And I said ideal gas is a gas that behaves ideally at all temperature and pressure, which is for any given value of pressure, any given value of uh, of 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 volume, the gas must be equals to 1. The number of moles of that gas must be equals to 1. And from there again, I made mention of we have two kind of deviation generally. It's either it is a positive deviation or it is a what? A negative deviation. If the pressure is extremely high, which is, if this pressure here is extremely high, it will lead us to a negative deviation. And if the pressure is moderately, so we have moderately and extremely. So if this extremely, it will lead us to negative deviation, and if this moderately, it will lead us to what? To a positive deviation. But how can we even correct this deviation? How can we correct? So that is when this whole formula was introduced. So for correction of volume or pressure using that the ideal gas equation, for the ideal gas, like what I said, the pressure and the volume, which is the deviation, can be corrected. So for pressure and volume, for any deviation at all. Oh, sorry about that. I was having some glitch in my phone. It was giving me some issues, so I just have to like, because I'm the only cameraman at the same time, the tutor, so I have to like check to know if it is working or not. It's giving me some issues. So now back to this. I said we have positive deviation and then a negative deviation. Now listen, if you want to correct the volume for an ideal gas law, you use this formula. And if you want to correct the pressure for an ideal gas law, you are expected to use this formula. So the formula for correcting the volume for an ideal gas law is equals to V minus MB, while the formula for correcting pressure for an ideal gas law is P plus N square A all over what? V square. Whereby this A and B, they are Van der Waals constant. Please, they are Van der Waals constant, and this whole formula is for Van der Waals formula. That's Van der Waals formula. Correction of pressure, correction of volume. Why this a graphical representation of an ideal gas law? No matter what happens to the pressure or the volume, the number of moles will be equal to what? 1. But is it true that there is an ideal gas, a gas that behaves ideally at all temperature and all pressure? I don't know. So that question is for you. So let me just do a summary generally on the whole stuff. Then we leave this episode because I feel like my phone is giving me some tough time. So I really need to relax and then go through the phone. Okay, finally we have got to the last part of gas law or gas equation. So there are some things I wanted to take note of. One of them, 0 degrees Celsius is equivalent to 273 Kelvin. These are some of your examination questions. 1 atm is equals to 760 milliliters of mercury is equals to 760 torrent. Then the next thing, the standard entropy of a substance is heat entropy at 25 degrees Celsius and 1 atm. These are examination questions. They might leave these two spaces. They will tell you that the standard entropy of a substance is a dash. So your answer should be 25 degrees Celsius and 1 atm. 25 degrees, not 0 degree again, not 273 Kelvin. The standard entropy of a substance is usually 25 degrees Celsius and what? 1 atm. Then a negative deviation occurs due to moderately high pressure, while positive is due to extremely high what? Pressure. For real gases, if a gas behave ideally at all temperature and pressure, then PV all over RT is equals to what? 1, which is the number of mole of that gas is equals to what? 1. The next thing again, this Van der Waals equation, this very one here is used for the correction of pressure, while this one here is used for the correction of what? Of volume. Talking about this graph again, PV all over RT, here is 1, here is P, or here is what? V. So please take note of that. I want to ask you a question. We have K for Boyle's law. What is the meaning of the K for Boyle's law? What is the meaning of the K for Sharp's law? What is the value for K for general gas equation? And what is the meaning? Let me even stop there. K for Boyle's law, K for Sharp's law, K for all the constants. Please, I want to take note of them. But for the classes I'm beginning to use now, go to the comment section now. What is the constant for Boyle's law? What does it signify? What is the constant for Sharp's law? Or to make the whole thing easier, Joe's is a constant for dash. Option A, boys. Option B, Charles. Option C, Avogadro. Then option D, general gas equation. So Joe, is it for Boyle's law, is it for Charles, is it for Avogadro, or is it for general gas equation? If you know the answer, drop it in the comment section. Thanks for watching, and this will be our last video on kinetic theory of gases. If you love what I'm doing, why not hit the subscription bell if you have not done that, and don't forget to smash our like button. Don't forget to drop a comment in the comment section, and please, I'm begging, always share my videos to your loved ones, share it to your friends. Just share the video, because if you share the video, YouTube is going to recommend this account to others as well. And this is actually a free class, so since you are not paying, I want you to pay me as soon as possible. And how do I do that? Is for YouTube, is for you to recommend my video to others. So when you start sharing my link, when you start telling people about Guido Academy, YouTube will definitely recommend my video to others. Please don't forget, subscribe to Guido Academy. Hope to see you in our next episode. Sorry, our next season, because this is actually the last episode. Hope to see you there. Stay blessed.